Very good morning. My name is Komal from BSc Second Year Chemistry Honors. I am reading Inorganic Chemistry chapters Non-aqueous solvent for visual impaired student. Let me start the chapters. Most of the chemistry reactions are carried out in the solution, and behavior of substance also depend upon the nature of solvent. In the earlier days of development of chemistry, the reaction have been carried out only in the one solvent, namely water. Had been facilitated by its readily availability, easy of purification together with its favorable physical and chemical properties such as long liquid range 0 to 100 degrees Celsius, high dielectric constant 78.5, specific heat of volatilization, dipole moment, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can be therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent property of waters have hindered the development of non-aqueous solvent. The solvent other than water which are used for carrying out chemical reactions are called non-aqueous solvent. Attempts have been made to find some other substance which could behave as good solvents like waters. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example liquid NH3, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used in the present unit. We shall discuss briefly an important feature of non-aqueous solvents such as NH3 and SO2. Physical properties of solvent and their role in chemical reaction. The useful of a solvent is determined from its some specific property that may help to carry out the chemical reaction and separate the product more conveniently. Some of important physical properties of solvent are discussed below. Melting point and boiling point. Liquid range. The melting and boiling point of solvent determine the temperature range within which the solvent can exist in liquid state under atmospheric pressure. Since most of reactions in a solvent system are carried out in liquid phase, the melting point and boiling point give the temperature range within which the solvent is useful. The melting and boiling point for some common solvent are given in tables. Melting point and boiling point of some common solvent. Example: solvent H2O have melting point 0.0 degrees Celsius, boiling point 100 degrees Celsius, and solvent NH3 have minus 77.7 degrees Celsius and boiling point have minus 33.4 and melting point minus 77.7. And now SO2 sulfur dioxide solvent, melting point have minus 75.5 and boiling point have minus 10.2 degrees Celsius. It is clear from the above table that water has excellent liquid range 0 to 100 degrees Celsius at ordinary temperature and pressure. Acidic acids can also act as solvent at ordinary temperature, while NH3 and SO2 can act as solvent only at low temperature. Heat of fusion and heat of vaporization. The value of heat of fusion and heat of vaporization help to know the nature and strength of force which hold the molecule of the solvent together in the solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of substance to change from solid to liquid state is called a molar heat of fusion. Similarly, the heat of absorbed by 1 mole of substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the magnitude of molar heat of fusion and molar heat of vaporization give you us some insight into the nature and strength of the intermolecular forces, and these also determine the solvent properties. A better idea of intermolecular force in a solvent is obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is called Throsten constant. Delta H evaporation upon may T temperature is equal to Throsten constant. For normal liquid, if molar heat of vaporization are expressed in Kelvin and boiling point in absolute scale 0 Kelvin, then the Thomson constant had the value 21.5. Delta H evaporation are in joule. Thomson constant is about 90 for normal liquid. Such liquid exist as independent molecule without any bond between them. A higher value of Thomson constant indicate associated molecules. For example, common solvents like water, ammonia, hydrogen fluoride have Thomson constant value greater than 21.5 and are therefore associated liquid. The molecules of this liquid are polar. The associated of polars is due to tendency orientate themselves so that oppositely charged end of molecule come near to each other. The molar heat of fusion and vaporization of some solvent are given. The solvent water have molar heat of fusion is 6.0 kg per mole and molar heat of vaporization have 40.65 kJ per mole. Ammonia have 5.65 kJ per moles heat of fusion and 23.56 kJ per mole have heat of vaporization. The inspection of table 2 show that the value of molar heat of fusion for water and ammonia are almost same. This means that force which hold molecules together in water and ammonia are the same magnitude, dielectric constant. This property is a measure of the polar nature of the solvent and helps to estimate the solubility of polar or non-polar substance in the solvent. According to Coulomb's law, the force of attraction between two charged ions is given by force is equal to Q positive Q negative upon may E arc square. E is the electric constant, where Q plus and Q negative are the charge of the cation and anion respectively. R is the distance between them and E is the constant called dielectric constant of the solvent. If E is the large, the force F will be small. As a result, only a small amount of energy will be required to separate the ions and hence it will be easy to dissolve an ionic substance. Thus, in a solvent of high dielectric constant, the ionic substance will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compound will decrease. The dielectric constant of some common solvents are given in tables. Solvent S2 have 18.7 at 18 degrees Celsius dielectric constant and NH3 ammonia have 22.0 dielectric constant and sulfur trioxide have 17.3 etc. It is clear that solvents like HF and S2 are the good solvent for ionic and polar compounds because of their high dielectric constant value. On the other hand, solvents like ammonia and sulfur dioxide with small value of dielectric constant show decreased tendency to dissolve ionic compound and exceptly those containing multi-charged ions, for example carbonate, sulfate and phosphate are practically insoluble in liquid ammonia or liquid sulfur dioxide. Fourth property, dipole moment. The dipole moment is related to dielectric constant of solvent. An ionic solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bonds in the molecule. Greater the polarity of the bond in molecule, larger in its dipole moment. Solvents having high dipole moment have greater tendency to dissolve the polar or ionic substance. This is because of the fact that the greater polarity results in a strong bond between the solvent and the solute molecules, and large solution energy is released. This large solution energy is sufficient to overcome the lattice energy in the solute molecule and help in dissolving the solute. Viscosity. It is measure of the fluidity of the solvent. Solvent like water, ethyl alcohol, and carbon tetrachloride have low viscosity and are highly fluid and flow rapidly under ordinary temperature. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbon have high viscosity and flow at much lower rate at ordinary conditions. In solvent at a low viscosity, the operations such as precipitation, crystallization, filtration, etc. can be easily carried out without any difficulty. With increased the viscosity of liquid, increase the difficulty of such operation. Type of solvent. Non-aqueous solvents have been classified in many ways. The following are the important classification based upon the chemical properties of solvent. Protonic and non-protonic solvent. Second, acidic, basic or protonic solvent. Ionization and non-ionization solvent. Coordinating or and non-coordinating solvent. First, the protonic and non-protonic solvent. The solvent from which proton at positive ion can be derived are called protonic or protic solvent. Therefore, protonic solvent contain ionizable hydrogen at positive. Common examples are H2O, HF, H2SO4, HCN. The solvent from which proton cannot be ordinarily derived are called non-protonic solvent. These are also called aprotic solvent. In other words, these solvents do not contain ionizable hydrogen atom. Common examples are liquid SO2, N2O4, C6H6, CHCl, etc. Second, acidic, basic or aprotic solvent. This classification is based upon the acidic or basic behavior of solvent. The solvent which have a strong tendency to donate proton are acidic in nature and are called acidic solvent or protogenic solvent. For example, H2SO4, liquid hydrogen fluoride, acetic acid, etc. Solvents which have strong tendency to accept proton and are basic in nature are called basic or protophilic solvent. For example, liquid ammonia, pyridines, hydrogens, ethylenediamines, etc. The solvent which neither have a strong tendency to gain nor a strong tendency to lose proton are called aprotic or amphic solvent. In other words, they neither behave as strong acidic nor basic but can behave as acid as well basic depending upon the nature of reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Ionizing or non-ionizing solvent. The solvents which are capable of undergoing self-ionizations are called ionizing solvent. Some common examples: water, ammonia, hydrogen fluoride, sulfur dioxide, etc. These ions at below. H2 plus H2 at equilibrium product is H3O positive plus OH negative, etc. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbon, etc. These are non-polar or non-ionic in nature, coordinating and non-coordinating solvent. The solvent which are capable of coordinating with the metal ion or anions of the solvent are called coordinating solvent. For example, ammonia, sulfur dioxide, dimethyl sulfoxide, acetonitriles, formamide, nitromethane, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvents. For example, CCl4, saturated hydrocarbon, etc. These are not much interact in inorganic chemistry. Type of a reaction in non-aqueous solvent. The following type of reaction commonly occur in non-aqueous solvent. First है metallurgical or precipitation reaction. The reaction in which precipitates occur on mixing two solvents are called metallurgical or precipitate reaction. These type of reaction can be preceded if the value of solubility product of the common compound formed in the solvent are known. These values depend upon the nature of solvent used. For example, in water, silver nitrate and barium chloride react to give a precipitate of silver chloride, leaving barium nitrate in the solution. On the other hand, in liquid ammonia, a precipitate of silver chloride combined with barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. Therefore, reversible of a chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can be precipitate in liquid ammonia. Water-soluble copper sulfate may be precipitate in anhydrous acetic acid. Salt formation. The reactions between appropriate acidic and basic substance to form salt are called salt formation reaction. In such case, the solvent used must be one in which the appropriate acid and base can exist. For example, sodium uride cannot be prepared by the reaction of urea on sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salt of urea is unstable in water and urate ion will take a proton from water to form hydroxide ion. Sodium urate react with water, then formation of a Na positive OH negative plus urea. However, this salt can be easily formed in liquid ammonia solutions by the reaction of urea with strong base soda amide. Urea reacts with soda amide in presence of liquid ammonia, then formation of sodium uride plus ammonia. Acid-base reaction also can say neutralization. The acid-base reaction in non-aqueous solvent can be explained on the basis of solvent system concept. As already learned, according to solvent system concept, an acid is a substance that by direct dissociation or reactions with the solvent give the cation characteristic of solvent. Similarly, a base is a substance that gives the anion characteristic of the solvent. The acid-base behavior of a substance depends upon first, the acid-base nature of the solvent, second, the characters of the solvent, and third, the solute-solvent interaction. In this case, the protonic solvents cations is the solvated proton and the Bronsted protonic concept is the same as the solvent system concept. For example, in liquid ammonia solvent, NH4 positive ions act as acid and NH2 negative ions act as bases. The neutralization reaction is acid plus base at liquid ammonia is equal to salt plus solvent. In non-aqueous, in non-protonic solvent such as benzene, carbon tetrachloride, lavish acid base type of reaction can occur because of non-ionization of solvent. The acid-base behavior of solvent in a solvent depend upon the acidity or basicity of the solvent. For example, acidity and behavior as show acid in ammonia, weak base acid in water, but a base in sulfuric acid. So, fourth, sololytic reaction or solubilized. The reaction in which the solvent molecules react with the solute in such way that the solvent molecules split up into part one or both which get attached to the solute molecules or ions are called sololytic reaction. Since these reactions occur through self-ionization of the solvent, the concentration of either of the cation or the anion is changed. For example, the sololytic reaction in water, ammonia, and ethanol are given below. Water as solvent, water at equilibrium at 3O positive plus OH negative auto-ionization can take place. Ammonia also take place auto-ionization. Alcohol भी take place auto-ionization. It may be noted that in case of a solvent like water, ammonia, alcohol, acetic acid, etc., the terms hydrolysis, ammonilysis, alcoholysis, and acetolysis are used respectively. Solvation. The reaction in which the molecule of solvent get attached to a solute species, cations, anion or molecule are called solvation reaction. The species formed in called solvate. The solvation reaction is called ammonia, alcohols, etc. are called hydration, ammoniation, alkylation, etc. and the result solvent are called hydrate, ammoniate, alcoholate, etc. For example, CuHO4 plus NH3 formation of product is ammoniate. Solvation of a cation occurs through ion dipole interaction between the positive cations and the negative end of a dipole or through coordinate bond in which the solvent molecule donates a pair of electrons to the cation. On the other hand, solvation of anions occurs through ion dipole interaction between the negative ions and the positive end of the solvent dipole or through hydrogen bonding in case of solvents such as water, ammonia, or hydrogen fluorides. It may be noted that certain cases it is difficult to distinguish between solvation and solvices because in many solvitic reactions the first step consists of solvation reaction. However, the term solvation is used for those reactions in which the solvent molecules remain in the resulting product. Let us discuss some reactions in two common non-aqueous solvents, liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solvents. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of its physical properties resemble those of a water's. Freezing point ammonia have 77.7 and water have 0. Boiling point ammonia have minus 33.38 but water have hangers. Density ammonia have 0.68 and water have 1.0. Dielectric constant have 22.0 ammonia and water have 78.5 etc. Comparison of a property of a liquid ammonia and water. The comparison of a property of a liquid ammonia and water reverse the following point. Liquid range. The melting and boiling point of liquid ammonia are lower than those of a water. In liquid ammonia, the liquid range is from 77 to minus 30 degrees Celsius, and therefore it presents some handling problem. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handling in cooling vessel, and nowadays a wide range of techniques have been advanced for handling it. Hydrogen bonding, like water, liquid ammonia is an associated solvent with hydrogen bonding because it contains a strongly electronegative element nitrogen. However, ammonia molecules are less strongly associated because nitrogen is the less electronegative than oxygen, and therefore NH make hydrogen bonding and bond is weaker than OHO bond. As a result, the freezing and the boiling point of ammonia are less since ammonia is less associated than water. It is better solvent for organic compound. Dielectric constant. The dielectric constant ammonia is lower as compared to water. Suggestion is lesser tendency to dissolve ionic compound. Liquid ammonia and therefore a pure solvent for ionic substance. Soluble salt include most ammonia salts, nitrates, thiocyanate, and iodides. Fluorides and many oxysalts are generally insoluble. However, ammonia has lower viscosity than water and might be expected a promoted greater ionic mobility and therefore compensate to some extent of the effect of dielectric constant. Self-ionization. Both ammonia and water show comparable self-ionization as represented below. NH3 at equilibrium, NH4 positive ammonium and ammonium ion plus NH3 at equilibrium is equal to ammonium ion plus amide ion. However, the extent of autoionization of liquid ammonia is less than that of water. This is clear from its lower specific conductor and lower ionic product. KNH3 is equal to NH4 positive NH2 negative concentration is equal to 1.9 into 10 to the power minus 23 at 50 degrees Celsius. Ammonia can conduct electricity to a feeble extent. Feeble means ammonia is a better solvent than water. The following properties of ammonia make it a better solvent than water. Liquid ammonia is very pure conductor of electricity. The specific heat of ammonia is more than that of a water because of a low. Liquid ammonia is less viscous than water. Most of salt when dissolved in liquid ammonia conduct electric current better than the water. This is not due to ionization powders of ammonia, which is the power of ammonia, but due to low viscosity, which greatly increase the mobility of ions. Liquid ammonia is high critical temperature and pressure. It is less associated than water due to less hydrogen bonding. Therefore, it is a better solvent for organic compounds. Liquid ammonia forms strong reduction metal ammonia solution with alkali metals. Therefore, it is an excellent solution in water's reduction reaction. Reaction in liquid ammonia. As mentioned earlier, ammonia is water-like properties as a solvent. It is therefore expect that the reactions which take place in aqueous solution can also occur in ammonia solution. Some of the important chemical reactions occurring in liquid ammonia are given below. Acid-base reaction. The acid-base reaction in liquid ammonia can be easily understood by comparing the reactions in water. According to solvents, the system consists of acid and base, the substance producing H3O positive ion in water act as acid, while those producing OH negative ions act as basic. Liquid ammonia ionized as. Therefore, the substance producing ammonia ions in liquids, ammonia behave as acids, while those producing amide ions behave as bases. For example, ammonia salts such as ammonia halides, thiocyanate nitrates are soluble in liquid ammonia and behave as acid. Similarly, amides, imides, and nitrites behave as a basic in liquids NH3. The chemistry base in liquid ammonia is potassium amide KNH2, which ions are lithium amide, sodium amide, and alkalines earth metals amide have a very low solubility and therefore KNH2 in the chemistry base in liquids NH3. Proteolysis contain compounds like urea, acetic sulfides, etc., which are incapable of donating proton to waters can readily donating proton to NH3 in liquid ammonia. These reactions are called proteolysis reaction, hence these compounds act as a acid in liquid ammonia. Sulfide acid behave as a dibasic in liquid ammonia. Sulfide acid behave as dibasic in liquid ammonia. It behaves as a monobasic in aqueous solution because NH2 group cannot donate a proton to water. Sulfamic acid behave as monobasic in aqueous solution. Acid-base neutralization. In aqueous solution, the process of neutralization of a strong acid and a strong base involves the combination of NH3O positives from acid and OH from base to form a practically unionized water. For example, the neutralization of a hydrolyzed acid and the sodium hydroxide may be expressed as. In a similarly way, the neutralization of acid and basic in liquid ammonia involves the combination of NH4 positive ions and NH2 ions. There are many examples of empiric behavior in liquid ammonia. The compound that dissolves water in acid and base are called empiric solvents, a substance. For example, in liquid ammonia, zinc amide show empiric behavior analogous to the zinc hydroxide in aqueous solvents. Thus, acid give NH4 positive ions and base give NH2 negative ions in liquid ammonia. These are termed as ammono acid and ammono base. Reaction of a ammono acid. Ammono acid is a substance that furnishes NH4 positive ion in liquid ammonia. Ammonium halide nitrate or thiocyanate are very soluble in liquid ammonia, giving NH4 positive ions and therefore concentration solution act as a ammono acid. We know that acid give hydrogen with metal in aqueous solution in a similarly way that ammono acid, ammonia, salt in liquid, NH3 reaction with alkali and other metal is given hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolve many metal oxides similarly to their behavior in aqueous acid. Reaction of ammono base. Ammono base is a substance which is liquid ammonia solution give NH2 negative ion. The commonest base in potassium amides, which is much more soluble than lithium and sodium amides. Metal salt react with ammono base to give amides, and nitrides with great precipitate in liquid ammonia. Precipitation reaction involve double decomposition because of the difference in the solubility of various substances in waters and liquid ammonia. A large number of precipitation reactions which are not normally possible in water have been reported to occur in liquid ammonia. For example, silver chloride in precipitate in aqueous solution as. Similarly, a white precipitate of BaCl2 is produced while solution of silver chloride and barium nitrate in liquid ammonia are brought together. Lithium chlorides may be precipitated by the reaction and ammonia chloride and lithium nitrate in liquid ammonia Iodides and bromides create precipitate Vahan solution of bright nitrate and ammonia halides in liquid ammonia are mixed together. Many metal sulfide can be precipitated in liquid ammonia by ammonium sulfide from the nitrate solution of this metal. Ammonolysid. The solvolysid reaction in liquid ammonia are called ammonolysid and ammonolytic reaction. These are the analogous to the hydrolysis reaction and involve the attachment of ammonia ions or amide ions in the reaction. For example, hydrolysis of SiCl occur as SiOH means silicic acid. It may be noted that in ammonolysis atoms or ions from a substance is replaced by a nitrogen containing ions or radically minus NH2 or double bond NH or triple bond H. Some ammonolysis reactions are sulfurily chloride react with NH3 ammonia, then formation of a product sulfamide and NH4Cl. In excess of a liquid ammonia, ammonolysis of a TiCl to occur in stepwise Vahan. Organic halides which undergo slow ammonolysis are ammonolysed at boiling point of liquid ammonia. Mixture of primary, secondary and tertiary amines are obtained. Thought ammonia molecule is basic and has strong tendency to accept proton and therefore it will act as a basic. However, towards a very strong base, it as a boson donor. Example of this type of ammonolysis reactions are complete complex formation reaction. Many complex formation reactions is liquid ammonia are reported with are similarly to reactions occurring in the aqueous system. For example, zinc nitrate reacts with potassium amide to form insoluble zinc amides which dissolve in excess of amide due to formation of a complex compound zinc. Formation of ammoniate. Just as water forms hydrate, ammonia also forms ammoniate with many inorganic salts in this compound. The ammonia molecules are coordinate to the cation. Some typical ammoniates are BF3 react with ammonia in presence of liquid ammonia, then formation of a BF3.NH3 redox reaction. Liquid ammonia acts as an excellent medium of a redox reaction in liquid ammonia. The oxidizing action of a strong oxidizing agent is weaker than in water solution. For example, HNO3 in liquids, ammonia does not act as an oxidizing agent. Similarly, KMNO4 in liquids, ammonia acts as a weak oxidizing agent. On the other hand, reducing agents show increased reactivity. For example, Al3 metal acts as a very powerful reducing agent in liquid ammonia. For example, sodium metal in liquid ammonia reduce CuI to Cu, KMnO4 to K2MnO4 etc. Solution in liquid ammonia. The dielectric constant of a liquid ammonia is low, therefore it is expected to be poor solvent for ionic substance. Amongst the inorganic compound, all the ammonium salts, nitrate, thiocyanate and iodines are soluble in liquid ammonia. Oxide, hydroxide, carbonate, phosphate, sulfate and most of sulfide are insoluble. Most fluoride are insoluble in liquid ammonia and the solubility amongst halides increase. Most of the iodides are soluble. Calcium and the zinc chloride while are extremely soluble in water are quite insoluble in ammonia. Organic compounds such as halogen compound, alcohol, ketone, ester, simply ethers, phenols, amide, in nitro compound, etc. are readily soluble in water. In liquid ammonia, aromatic hydrocarbons are sparingly soluble. Paraffin and benzene are soluble. Amongst the element metal like Mg, germs are only slightly soluble in liquid ammonia. Alkali metal and alkaline earth metals are highly soluble in liquid ammonia. These four very interesting soluble are discussed below. Non-metal like Sp, I, Se are soluble in liquid ammonia. Solution of a alkali metal in liquid ammonia. The most distinctive property of a liquid ammonia is its ability to dissolve alkali metal. The resulting solutions are blue and extremely good electrical conductor. The important characteristics of alkali metal solution are: these are blue in color and the color is independent of a metal's dissolved when the concentration of a metal is increased. The color change to bronze and show metallic appearance. These solutions are conducting and show strong reducing properties. These solutions are paramagnetic and the paramagnetic character decrease with the increasing concentration. The reagents are pure and dry. Sodium solution in liquid ammonia are stable and can be pressured for several days. When alkali metals are dissolved in liquid ammonia, they ionized to give metal ions and valence electrons edge. Both the alkali metal ions and electrons become solvated by the ammonia molecules. The ammoniate electrons are responsible for blue color of the solvent. This is due to the absorption of visible light by ammoniate electron. The electrical conductance is also due to the ammoniate cation and ammoniate electrons. The conductivity of a metal in liquid ammonia is comparable to that of aqueous solution of a typical ionic compounds. As the concentration of a solution is increased, the ammoniate cation and electron association resulting in a decrease of a conductivity. Very dilute solution of alkali metals in liquid ammonia are metastable and when catalyzed they are undergo decomposition. As the concentration of a metal increases, the blue color changes to bronze and finally the blue color disappears altogether. This is due to the fact that impurities such as iron oxide catalyze the conversion of a metal into amide. On evaporation, the alkali metal ammonia solution alkali metal can be recovered. The strongly reducing characteristic of this solution is due to the presence of a readily available electron. The important application of alkali metal solution in organic chemistry is the reduction of a many functional group and unsaturated compounds. As already studied, the liquid ammonia is a thought-out study non-aqueous solvent. Some of its advantage and disadvantage of solvent are given below. Advantage of a liquid ammonia as a solvent. This solution of alkali metal without chemical reaction is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metal can be recovered from the solution by evaporation. The alkali metal solution are a strong reducing agent, even stronger than the hydrogen. Ammonia salt dissolved in liquid ammonia act as an amino acid, and these find application in pre-preparative chemistry. They can be used to prepare sealants, arsine, etc. The tendency of a solubilization in less in liquid ammonia than in water. Disadvantage of a liquid ammonia as a solvent. The liquid range for liquid ammonia is from -33.3 degree to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with liquid ammonia. Second, liquid ammonia has offensive odors. Therefore, it requires special technique to use it as a solvent and as a reaction medium. Liquid ammonia is hygroscopic in nature, hence all the reactions are carried out in skilled tube. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvents because it does not contain an hydrogen atom. It is also one of the important non-aqueous solvents and has been widely used in industry. Under normal condition of temperature and pressure, sulfur Dioxide is a gas, but it can be readily liquefied and is easily maintained in the liquid phase. It has a wide liquid range minus 10 degrees Celsius to minus 75.5 degrees Celsius and can be used as a solvent. It can be easily purified by passing the gas through sulfuric acid and thought P2O5 to remove trace of water. Its dielectric constant is small and therefore is a good solvent for covalent compound. The characteristic physical properties of liquid sulfuric dioxide. Structure of a sulfuric dioxide molecule. Electron, electron diffraction studies have shown that sulfur dioxides in gaseous phase have the angular structure as shown ahead. The valency bond they have predict that the SO2 molecule in a resonance hybrid of the following two resonating structure. Solubility of a compound in liquid sulfur dioxide. Among the inorganic compound iodines and thiocyanates are more soluble. In case of alkali metal halides, the solubility are in the order Mi greater than Mbr greater than Mcl greater than Mf. Yet the uninegative polyatomic anions such as ClO4 negative, NO3 negative, Bf4 negative, etc. are generally more soluble in liquid. SO2 salt of a multi-negative anions such as SO4 2 negative, SO3 2 negative, S2 negative, etc. are practically insoluble. Many of ammonium, thallium, and mercuric salt are soluble. It is an excellent solvent for covalent compound. Many covalent substances like halogens, interhalogens, phosphorus halides, oxyhalides of sulfur, etc. halides are soluble in it. Metals are insoluble in liquid SO2. Among the organic compounds, aromatic hydrocarbons and alkenes have very highly soluble in liquid SO2 in comparison to saturated hydrocarbon, pyridine, quinine, ether, halogens, derivative, and acid chloride also dissolve in liquid SO2. Many compounds dissolve in liquid SO2 due to solvent formations, for example, Ki4SO4, CaI2, 4SO4, etc. Many donor molecules are follow stable solvent with SO2. Autoionization of SO2. Pure SO2 is a pure conductor of electricity, thought it is a blade to autoionization. The thionyl ions is analogous to the hydronium ions and ammonia ions, and sulfide ions correspond to hydroxyl and amide ions, aqueous ammonia system respectively. Reaction in liquid sulfur dioxide. Some important chemical reactions in liquid sulfur dioxide are discussed below. First, acid-base reaction. Liquid SO2 undergo autoionization as according to solvent system concept of acid and base. The compound which give thionyl ions SO2 negative in solution of SO2 would behave as acid, where compound giving sulfide ions and liquid SO2 would act as a base. For example, compounds such as SOCl2, SOBr2, etc. act as acid in liquid. On the other hand, calcium sulfide increase the concentration of a sulfide ion and therefore behave as the base. Amphotic behavior is shown by the zinc and aluminium ions. For example, react with SO2 negative ions in liquids SO2 to form insoluble aluminium sulfide. If the precipitate is treated with the excess of sulfide, the precipitate is dissolved. Solvolytic reaction. Solvolytic reaction in the liquid sulfide dioxide are not common as there are other protonic solvents such as NH3. Some reactions are given though ammonia acid is solvolized in liquid SO2. The reaction is analogous to the reaction of ammonia acetate in waters. Contains covalent halides such as PCl5, PBr5, UCl6 undergo solution in liquid SO2 is sealed tube. Many binary halides such as HbCl3, HbCl5, SiCl4, etc. do not undergo solvolysis in liquid sulfuric dioxide. The formation of a solvent dilution compound with the solvent are also known. Precipitation reaction. A large number of a precipitation reaction can be carried out in liquid sulfuric dioxide due to selective solubility of compound. The precipitate of several insoluble compound in liquids sulfur dioxide can be carried out by treating them with soluble compound in sulfur dioxide. Some of these are for HbCl3 plus 3Lii at liquid SO2 form the product of HbI3. Fourth, complex formation reaction. A large number of complex ion formation in liquid sulfur dioxide have been reported. For example, solubility of iodine in liquid sulfur dioxide is greatly increased by the addition of potassium or rubidium ion in the iodines. This is due to the formation of a complex Ki3 or RbI3. Similarly, the increase in the solubility of a cadmium iodine and mercury iodine in liquid sulfur dioxide in attribution to the formation of complex organic reaction. A large number of organic reactions have been carried out in liquid sulfuric dioxide because organic compounds are soluble in it and it is relatively inert solvent. Some examples: sulfonation of aromatic hydrocarbon by sulfur dioxide or chlorosulfuric acid. It is also used as a solvent of addition of a substitution of a bromine reaction. 6. Sulfur dioxide of a crystallization. The reactions are also called solvation reactions like waters and ammonia. Salt having sulfur dioxide of a crystallization have also been observed. Some example: NaI.4SO2, Ki.4SO, etc. These are formed with a highly soluble salt and are analogous to hydrates. Redox reaction. Both gases sulfuric dioxide behave both as an oxidizing and a reducing agent. Liquid sulfur dioxide does not show by any marked reducing or oxidizing tendency. It simply acts as a medium for the curtained redox reaction. For example, iodine is liberated from Ki in the presence of HbCl5 in liquid sulfur dioxide. Some special feature of a liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantage over other solvents as a reaction medium. Some of these are: it has a low boiling point and these allow easy evaporation and their removal from the reaction mixture. Second, it has low melting point and therefore it allows reaction to be carried out at low temperature. Third, liquid SO2 is an inert solvent. It has unusually solvating power for the both covalent and electrovalent compound. Fifth, it is a better medium for covalent compound like hydrocarbon and it used for the purification of some petroleum product. Sixth, it is used as a dilute for the superacid mediums which help in the reducing its viscosity without affecting in its acidity. Thank you.